It's a real pleasure to open the session with Rich Schwartz from Brown University, who's going to tell us about Pappus' theorem, the modular group, and patterns of geodesics. Rich.
Okay, it's great to be here. So, in the end, I want to talk about some group actions on a non-positively curved symmetric space, and it's I'll kind of start slow and build up to it, but the way it works is there's kind of an analogy between Ferry addition and something called Pappus' theorem. And then Ferry addition leads to various things like the Ferry triangulation in the hyperbolic plane and the modular group action. And then this is going to lead to patterns of geodesics in a higher rank symmetric space and group representations. So I'll start just by talking about, I'll kind of go back and forth between these things, and I'm also going to maybe show a quick animation. Okay, so Ferry addition, this is, some people, in the 4th grade, this is how some people add fractions, but you wouldn't be at the Isaac Newton Institute or something. You did anyway. A and B are supposed to be relatively prime and integer numbers, and you add them like that. And on the other side, Pappus' theorem, you start with 6 points distributed on 2 lines, and then you connect them up like this. And then the theorem is that these 3 points lie on a line. So these things are kind of similar because the input here is two fractions and the output's a fraction. And here the input is 2 triples of points and the output is a triple of points. So you might get the idea that you could iterate this. And I'll show this on the left. I mean, the way you usually do this is you think of, usually the good input is 0 and 0 over 1 and 1 over 1, and then when you do this you get 1/2 and then 1/3 and 2/3, and it goes on like that. And the good way to think about this is that this is the real line, the ideal boundary of the upper half plane, and then you should connect these with semicircular arcs, and this produces an infinite pattern of geodesics in the hyperbolic plane. And then you should also sort of go outward as well as inward, and this will produce the familiar tiling of the hyperbolic plane of the Ferry triangulation. And then there's a group action that acts on this space. It's Z mod 3 free product Z mod 2, and it's the group of orientation preserving hyperbolic isometries of this picture. So the Z mod 3 elements are you could take a generator to be the order 3 rotation symmetry of one of these triangles, and then the order 2 generator to be, and maybe it's better to put it up here. It's there's a rotation by 180 degrees, which maps the inside here to the outside here. And these generate a copy of the modular group, and the modular group just permutes the geodesics in the Ferry pattern. And if you take oriented geodesics, then the modular group acts simply transitively on the oriented geodesics. So that's a picture of the modular group that kind of comes in a way out of Ferry addition. So let me sort of connect this to Pappus' theorem in a special case. So what I want to say is that for one particular case of Pappus' theorem is really in a sense, a copy of this operation. So what you do is you, well, okay. You put your two lines like this, and you pick them to be vertical, and you pick the points to be at the midpoints of the edges, and you center them, the first at 0 and the second at 1, and then you do the operation, and this didn't quite work out, but it turns out to be vertical, and then you do it again, and it keeps going like this, and you actually generate the fractions in the same pattern. So this is really kind of a geometric way to construct. It sort of mirrors Fourier addition, but because this is you have freedom with Pappus's theorem. You can sort of tilt the lines or move the points up and down, and then you'll see something different. So this is sort of the typical thing you would do, like in I don't know, for group representations, where you have sort of one particular group, and then you sort of include it in a larger family. So Fourier addition kind of includes in Pappus's theorem. So I'm going to demonstrate this. This picture over here, what I'm showing you, what's on the screen is kind of these two quadrilaterals, or you start like with the big quadrilateral, and then you get two more, and then when you iterate again, you're going to get two more quadrilaterals. So I'm going to just push the button and show you this in action. So that's what you see, but there's a parameter, so you can vary this around. There's a sort of a two-parameter family of things you get. There's some, if you look at this carefully, you sort of see that there's a kind of a curve that goes through the middle of it. All the center points line up. In this case, they just make a straight line, copy the interval. But here, there's actually the points limit on a continuous curve. So this is a picture. You can also make kind of an artistic one. Okay, so in general, when you do this, doing this operation over and over again is really a semi-group, because you can sort of subdivide either on the left or on the right, and then you can iterate this, and you'll get an interval. So I want to explain how you actually can turn this into, how you sort of go, just like in this picture, you can go outward as well as inward. I'm going to explain here how you can kind of generate a larger union of these. I really think of these as boxes. So the input for the construction is a quadrilateral with two points on the top and 1 point on the top and one on the bottom. And this is supposed to be the input for Pappus's theorem. And then so if this is the original marked box, I don't know, say A or something, then when you do Pappus's theorem, and this is T of A, and then B of A, and then the semigroup generated by T and A gives this picture. And then there's also a third operation. What you do is you take your box, and now you think of this as living in the projective plane, which is just the space of lines to the origin in R3, and I'm drawing in just the usual affine patch. And if here's the box A, and then I use this diagonal like so, and so I'll shade in A. This is A, and then this up here is I of A, and I of A doesn't, and this is also I of A down here. It doesn't look like it's. I want to start with convex quadrilaterals. This doesn't look convex, but it's a convex quadrilateral in the projective plane. It goes like this, and then it goes around and then back up and over. So this gives you these elements, I, T, and B. They generate a group, and you have various relations like TIT equals B, and BIB equals T, and TIBI equals identity. I won't write them all, but the group turns out to be, again, the modular group. So you sort of have there's a modular group that's acting on this in a kind of combinatorial way. Okay.
These are projective maps?
No, these are just completely combinatorial things. They just but then what you could do is you have this collection of these boxes, and you'd like to get an honest projective geometry action on them. So what you do is so you start with one of these marked boxes. Say A, and then you look at the whole orbit. So this is just, you just apply this whole group action to A, group to A, and then you notice something. Now I'm going to get back to hyperbolic geometry, so or something like it. So the projective plane, you have the usual group of projective transformations of the projective plane. These are maps which, they're homeomorphisms of the projective plane that map lines to lines. And you have a second kind of map of the projective plane, which is the dualities. These map lines to planes, lines to points and points to lines. In terms of, if you think of projective plane is the space of lines to the origin, and the set of lines in the projective plane is the space of planes to the origin. And then an example of the duality maps each line through the origin to its perpendicular plane through the origin. This is a map. So these dualities don't act as homeomorphisms of the projective plane, but they map the projective plane to its dual. So, and they act as homeomorphisms on the flag variety. So the flag variety is the space of points and lines in the projective plane where the point is on the line. And if you apply a duality, it maps the point to a line and the line to a point, and it turns out to be a homeomorphism of the flag variety. So the thing you notice, here's the thing. The first thing that turns out is if you look at if you look at I of A, B of A, and T of A, then there's an order 3 projective transformation that cycles them, that maps this to this and this to this and this to this. And that's like the Z mod 3 in the, where did it go? So I'm trying to construct now a modular group action on this orbit. So that you get the Z mod 3. Anytime you have one of these boxes, there's a projective transformation that permutes them. And now I'll just, okay, so first I'm just going to lie. This will simplify things tremendously. If you just, so here's the lie, that there's also an order 2 projective transformation that maps A to I of A. And then if you think about it in terms of the picture, this one is really doing like the order 3 rotation, and then this one is like doing the order 2 rotation. Unfortunately, it's not quite true. There's no projective transformation that maps A to I of A. But it turns out in Pappus's theorem, it looks like it's a theorem that involves 6 points distributed on 2 lines. But you can also think of it as involving 1, 2, 3, 4, 5, 6 lines going through 2 points. It's a theorem that's completely self-dual. So you have to imagine that these quadrilaterals, they have kind of partners in the dual plane. Each one in the projective plane defines one in the dual plane, which is like a doppelganger. And whenever you do the 3 operations on the original one, it's just the same as doing them on the one in the dual space. And then this map I really, there is a duality that maps any one of these boxes to its doppelganger as order 2. So so this gives you modular group action on, if you like, the flag variety. And you can see in this picture, like you've got this is like the limit set of the group in the projective plane. And if you look at it, the lines of the boxes, the tops and bottoms of the boxes produce a line field. You can kind of see these lines. And so you not only do you have a curve of limit set as a curve, but there's also like a line field. And so you really have a limit set which is like a loop of it's like a loop, a continuous loop in the flag variety. So and the group, it turns out to be a discrete group, and there's a domain of discontinuity, and the quotient turns out to be the trefoil knot complement. So this was stuff I did. This is more than 30 years ago, and it turns out to be kind of very, very close to what happens for Anosov groups. These are sort of like, these nowadays are called relatively Anosov divisions. But what I want to do now is, the thing that I could never figure out before was, like, if you look at this picture, you'd like to sort of like snap on, like you'd like to sort of think that like this big box corresponds to a geodesic, and then this one, like you'd like to just sort of informally attach arcs to these boxes and kind of reproduce the fairy pattern in some combinatorial way. So the thing I realized this year was how to do this in the symmetric space. And then I got some more results about this kind of stuff. So what I'm going to do now is I'm going to explain something about the symmetric space that's underlying this, and then I'll explain how you see this kind of pattern as a pattern of geodesics inside the symmetric space, and then I'm going to talk about things like bending and shearing, and then what my theorem is. My theorem is a classification of one of the Barbeau component of modular group representations. So I'm going to sort of get to the theorem, but first I'm going to just talk about the anatomy of the symmetric space. And so there's going to be some talk about symmetric space, and then I'm going to hook it back up with that stuff. Okay, so the symmetric space X is SO3, it's SL3R mod SO3. And both projective transformations and dualities act on this space as isometries. And I'm going to, so one way to think concretely about X is it's the space of unit volume ellipsoids centered at the origin in R3. And then SL3 naturally acts on this. If you apply a linear transformation to an ellipsoid, you get another one. And the stabilizer of the round ball is just SO3. So this space is just naturally bijective with the cosets in this. I mean, the equivalent way to think about this is like the determinant one positive definite matrices. And the way to go back and forth is you take a matrix and then the ellipsoid is the unit ball and vice versa. So X is a 5-dimensional space, and so this is X, this is boundary X, and it's so high dimension it's hard to draw, but I'm going to show you that in the boundary of X there's a copy of the projective plane, and also a copy of the dual projective plane, and also a copy of the flag variety. Flags. So I'll do this. So what is the boundary? The ideal boundary, it's the visual boundary. You just pick the origin in the space and you look at just all the geodesic rays. This has a metric of non-positive curvature. And you just, the ideal boundary is just the space of rays, and if you're at a different point, there's a, for each ray through a different point, there's a unique ray at the origin, which stays at boundary distance from it. So this sort of gives you a way to define this so that the group of isometries extends naturally to ideal boundary. So let me show you how to see the projective plane in the boundary. I'll use food analogies. So first think about a noodle. Imagine you have a ball and you degenerate it, and it becomes long and thin. So in the limit, it defines a line through the origin. That's a point in the projective plane. How do you think about the dual projective plane? Well, you could take a unit ball and you could turn it into a pancake, make it long and thin, and then you, not, just make it round and flat, and that defines a plane through the origin in R3. So this is a copy of dual projective plane. Then for the flags, you think of taking your ellipse and making it look more and more like a popsicle stick. So in other words, like it's, gets infinitely long and it gets infinitely thin and its width stays about 1. And the long part's defining the line, and then the kind of flat part is defining the plane that contains it. So in this way, you can kind of see all three things, all three subsets in the boundary of the symmetric space. The rest of the symmetric space is sort of like, it's some kind of hybrid between, like, you could have an ellipse array where the ellipsoids are sort of mostly noodle-like, but a little bit popsicle-like or something, or they could be like mostly pancake-like, and so somehow if you remove the projective plane and its dual, then the whole thing just deformation retracts to the projective plane. So that's the first thing I want to say. So the isometries of X act on, they're either projective transformations or dualities, and they act on X in such a way that they always preserve the flag variety, and they either preserve or swap the projective plane and its dual. So this whole picture, this iteration of Pappus's theorem, it's really living in the ideal boundary of the symmetric space. And so what I want to do to get a nice pattern of geodesics is try to join things together in the symmetric space. So that's what I'm going to, just looking at the clock, 25 minutes, I guess. Yeah,
I think it's counting down, not up. 36, including
36 minutes. Oh, great. Okay. All right. So I want to talk about connecting points in the ideal boundary of the symmetric space. And unlike the hyperbolic plane or space of negative curvature, you don't have unique geodesics joining points in general. So there's this space has rank 2. There's a copy of the Euclidean plane inside the space, and it corresponds to the diagonal matrices. Equivalently, it corresponds to the ellipsoids of the form x over a squared plus y over b squared plus z over c squared equals 1, etc. So just the ellipses that are kind of aligned with the coordinate axes, that subset is a flat in this symmetric space. And so this is a copy. This is a copy of R2 sitting inside X. And this is the origin. It corresponds to the round ball. And then you can let one of the directions go to infinity and the other go to 0. And this corresponds to a line that will land in the projective plane. It sort of goes like this. This way, these things are getting long and thin. And this way, they're turning into pancakes. So one end of this geodesic goes to the projective plane, the other end goes to the dual projective plane. But you could also let the second one go to 0 to the third one. And so you get this familiar hexagon. And the picture alternates between P and dual, P dual, dual. And then the geodesic, this is the vial chamber, and the geodesics in here, the ones that go right down the center, they're the ones that land on the flag space. They're kind of halfway between. So you have these other directions, which in the center, they all go to the flag space. So somehow the picture alternates, and that's what, these are the, these these are like the kind of singular geodesics in the space, and then these that go down the middle, or you might call them like medial geodesics, that on either end they land on flags. So if I have a pair of flags, and this picture, it's a symmetric space, so a picture like this exists at any point, and at any point within the flat. So these medial geodesics, the one that go right down the center of the vial chamber, they determine a pair of flags. But a pair of flags doesn't quite determine one of these geodesics, because just to draw the same picture again, you have a foliation by parallel medial geodesics, and all of them limit on the same flag. So if you have a pair of flags in the boundary, it really determines a foliated flat. It's a flat with a foliation by medial geodesics. So now I want to say one more thing about the symmetric space. The nicest kind of isometries that are not projective transformations are the ones where you just fix a point and you reflect and you reverse all the geodesics through the point. Those are called the point reflections. And remember that I talked to you about this duality given by the dot product, where you take each line through the origin to the plane through the origin, and that duality acts as a point reflection through the origin in the symmetric space. And any other duality like that, conjugate to that, acts as a point reflection. Those are called the elliptic polarities. So again, the elliptic polarities are point reflections through points. Okay, so now let me go back to the symmetries of Pappus' theorem. You have this is a marked box. Then you have, well, I'll just say it like this. Here's your marked box, A, and here's a flag. So each marked box determines a pair of points in the ideal boundary in the flag space. And so each marked box determines a foliated flat because it has a pair of flags. And if I do Pappus' theorem, then the next one in defines two more foliated flats. So in the symmetric space, you have this whole orbit of boxes, and each box determines a foliated flat. So you get this pattern of foliated flats inside this symmetric space, and they're organized just like the fairy triangulation. Like these like the ones corresponding to this, this, and this, they make like a prism. I'll try to draw this in the symmetric space. So this slightly misleading picture. So these are supposed to be flats, and each one is foliated. And this is a little bit misleading because the flats don't actually meet; they're asymptotic, just like in the fairy triangulation. So this is the structure you get, and then I prove that this is embedded. So you get this embedded family of prisms. Then there's one more piece of structure.
Can you say again, the prism corresponds to what object?
The prism corresponds to I of A, T of A, and B of A. In other words, each of these three boxes gives rise to a plane, and they're mutually asymptotic at each of the ends. So this produces a prism. There's something you can think of it as like an ideal triangle across a real line. And then I wanted to go one step further, which was I wanted to pick out a pattern of geodesics. So at the moment, there's no canonical choice of a geodesic that joins this flag to this flag in the symmetric space. You have this whole family. But then the lucky thing is, if you look at the map I, this duality that maps I to A to IA, you can just compute that this is one of these point reflections. And because it just swaps the tops and the bottoms of these things, it preserves the flat. And it just, so this element, the way it acts on the flat I'm talking about is, it just acts as an isometric 180-degree rotation. In particular, its fixed point is in the plane, and so this determines a canonical geodesic. So in this way, you can produce a kind of a copy of the fairy triangulation inside the symmetric space. So these things, they're kind of like higher rank pleated surfaces, because they're embedded. I mean, they're not really surfaces, but they're kind of patterns of geodesics. And if you take the marked box that I used in the beginning to just kind of mirror the fairy addition, then the pattern is contained in a geodesic plane inside X. But as you wiggle the points, you see some kind of bending. So, I mean, so you sort of see like this two-parameter. You can't really see it, but it's a two-parameter family of sort of like kind of bent copies of the fairy triangulation inside the symmetric space. Right.
Can you say again, if you have a plane, it looks like it should have 6 objects, 3 points and 3 lines, looking at the figure on the top.
You mean here?
Mm-hmm.
Yeah.
These points and the rows,
Well, so in this plane, you have these three different directions that you're cutting through the middle of the vial chamber, but only one of them is. I mean, when you pick these, when you pick this box, these 2 flags pick out one of the foliations in a canonical way, and the other ones are just irrelevant to the construction. Another way to say it is that a triple of points in a kind of triple of points in the projective plane, it defines a flat uniquely, because you could think of taking the matrices that have these as the eigenvalues, and that's like a conjugate of the diagonal matrices. But then there are 3 ways to pick out a pair of flags in the triangle, and each of the 3 different ways defines a different one of the 3 foliations.
So you have a prism, each prism is a plane, each plane is this triangle, and these triangles are where on the left?
So each prism has a foliation, and not only that, but it has a canonical fixed point in each one, and it comes from the point reflection that maps A to I of A, and so then you get there's a canonical way to choose a geodesic, the one that just goes through that point reflection. So not only do you have a prism for each triple like this, but you have a triangle. You have like an ideal hyperbolic triangle, each one. And then the order 2 element, it acts just like the modular group. Like the order 3 element just permutes the prism; it cycles it around. And the order 2 element would like just move this prism to the adjacent prism like that. I'm not drawing this very well, but if you look down on the picture, it just would the element. I mean, the element. This is the one corresponding to A, and this is the one corresponding to I of A. So the picture is you just kind of cross this with the reals, and then it goes like this.
So with the canonical ideal triangle determined by these fixed points,
yeah.
You don't mean it's really contained in a hyperbolic.
No. It's a triple of geodesics that are asymptotic at the 3 ends. That's right. Yeah, that's right.
So why is it that they're exactly asymptotic? So you have this canonical way of choosing a never maximal flat, why is it that when we take, let's say, that asymptotic triangle?
Yeah, why are they asymptotic? So because both of them limit on the same flag in one direction. Like the flat corresponding to this box and the flat corresponding to this box, they both in one direction they limit on this flag. What's that?
So you might have two rays that are asymptotic to a strip, and the way you draw it, it seems to be that the distance is, it's like in a hyperbolic plane.
Oh yeah, I'm not right. I guess I'm not. Yeah, I'm not saying the distance goes to 0. I'm just saying it stays a bounded distance away. Yeah, sorry. Yeah, that's right. I didn't.
Also bending even in that sense.
Yeah, so I didn't try to prove that they actually converge. I mean, and I don't know if they do, but they just stay a bounded distance. That's right. So another way to describe these groups is you can start with a prism. And you have an order 3 element. These prisms always have threefold symmetry, and this gives you an order 3 element. And then you can pick a point, just any point in the boundary of the prism, and then you can use a point reflection through that, and that will give you some kind of representation of the modular group. And so one of the things I proved is that every one of those is discrete and faithful. And it's either one of these Pappus groups or it's an Anosov representation. And this gives a complete classification of one of the components of the.
How do you prove it's faithful?
It classifies the Barbeau component. So now I'm going to say this a little more slowly. I'm going to go back and I'm going to talk about what happens in the hyperbolic plane. I'm going to talk about shearing in the hyperbolic plane, and then I'm going to talk about shearing in the symmetric space.
How do you prove it's faithful, Rich?
I'm going to explain. Yeah. That's the okay. So what happened was after I wrote this paper 30 years ago, Thierry Barbeau and Hee-Song Lee and Vivian Bellotti, they eventually wrote a sequel paper where they did the same thing with the boxes, but in their scheme of things, the boxes are they kind of retracted the boxes a little bit in a kind of invariant way, and so they get this kind of nested family of boxes where they limit onto a Cantor set. And their point was they wanted to say that my representations were the limit of Anosov representations. And they analyzed these very carefully, and they showed that they're discrete faithful because of a ping pong lemma argument. But they also showed that when the boxes get small, they not only do they get small, they get kind of long and thin. Their aspect ratio goes to infinity, and then this translates into the statement that they're Anosov. But they only proved it for a neighborhood of the ones I had. And what they did, I'm getting a little ahead of myself, is they had some construction where you start with one of the marked box orbits that I have, and then they modify it. And they used some funny matrix to modify it. It was like, I don't know, 1, 0, 0. And then there was like e to the delta, and then cosh epsilon. And the entries had some funny thing like this. And it's just terrifying matrix, and there's no way to compute with it. And so what I did was I realized that like cosh and sinh are just, you could just replace e to the delta with a, and cosh and sinh are just parameterizations of a hyperbola. So you could replace their construction with a rational parameterization, and then I just hit it with some computer algebra, some theory of resultants and things like that, and I was able to show that their entire family, that they actually exhaust the components. So I sort of show that their family is equal to the family you get from these prisms. So, okay, so that's kind of getting ahead of myself. But I'm going to go back and explain. So let me summarize what I said so far, and then I'll move on. So you can start with Ferry addition, and then you can use it to produce the Ferry tiling, the hyperbolic plane, and then you can look at the hyperbolic symmetries of it, and this gives you the modular group. Or you could start with a marked box, and you could iterate Pappus's theorem, or in this inversion operation, then you can look at its projective symmetries. This will give you a representation of the modular group into an isometry group of X. And there's a 2-parameter family, and then you can use something about the geometry of X to produce this copy of the Ferry triangulation inside X, except that it's bent like a pleated surface. So now I'm going to talk about a little bit about in answering Alan's questions I can talk about, but I'm going to talk about a little bit about shearing in the hyperbolic plane, and then I'm going to explain a higher rank version of shearing, where you can do shearing in a higher rank symmetric space. Maybe can people see over here? Is that okay? So in the hyperbolic plane, the theory each hyperbolic triangle has a kind of a distinguished point on it. It's where the inscribed circle touches, and equivalently, it's the just the fixed points of the group of symmetries of the triangle. And you can start with the theory triangulation, and then you can slide each triangle. Initially, these special points line up, but you can slide them so that there's some d distance between the points. And if you just do this everywhere in the same direction, this is called an earthquake or shearing. And a totally equivalent statement is you can take an ideal triangle, and you can take an order 3 element that is just the rotation, and then you can pick another point on here and just look at this order 2 element. And then the group generated by these two is going to be the symmetries of one of these sheared patterns. And so there's a kind of a ray's worth of shears, because you can move this point all along here. And all that's important is the distance between these points. And so it looks like you have a line's worth of shears, but the line kind of folds over itself. And the point at the end corresponds to the modular group. And as you go out, you're doing more and more severe shearing, and the limit set is a Cantor set, and it gets more and more sparse. So this picture is very much like what I said about the prisms. You pick a point at the center of the ideal triangle, and here you pick just an order 3 element, and then to get the order 2 element, you just pick any point on the boundary. And so this is kind of the analog of shearing in hyperbolic geometry. But there's another thing you could do, which is cusp opening. So cusp opening is that instead of taking an ideal triangle, you can take the geodesics and open them a little bit, and then you can just look at the group generated by reflections in the sides of this, and this will produce exactly the same family of groups. So sort of there's shearing and cusp opening, and they just give you the same family. So what Barbeau, Lee, and Bellotti did was they did this shrinking the boxes is the analog of cusp opening, they called it. And what I did was I identified what they did with here there's an identification between shearing and cusp opening. And so what I proved was that there's an exact identification between shearing and cusp opening. So again, what they do is they take the marked boxes in the orbit, and they shrink them, and then they look at the symmetries of that. It turns out that their operation is kind of weird. There's a 2-parameter family of ways to, so you have the marked box there's a 2-parameter family of marked boxes, and then there's a 2-parameter way of shrinking them. There's 2 parameters, epsilon and delta. And the other entries are like e to the minus delta cosh epsilon, and e to the delta sinh epsilon. Or maybe this is, something. Okay, well, they look like that without, I'm not going to get this quite right. But, so they have a 4-parameter family of representations, and there's, inside this 4-parameter family, there's a 3-dimensional surface where there's the extra duality. And they just solved some equation to do that, but they couldn't, they had to use something like implicit function theorem even to show that this thing existed. But then I was just able to compute it algebraically and show, what you show is that their representations of the modular group, on the boundary, they're just the copy of the Pappus group. So there's the character variety, or the moduli space for the Pappus representations, is a plane, and it's properly embedded inside just the space of all representations of the modular group.
You can't see the bottom unless you move.
Oh, sorry. let me go back over here. So you're looking at row this is your space, and you look at it modular conjugation. Turns out it's a three-dimensional space. Well, and the Z mod 3 element goes to order 3 rotation, and this one goes to a point reflection. So the space of these mod conjugacy just turns out to be homeomorphic to R3. And the Pappus representations give you an embedded and a properly embedded plane inside the moduli space. Maybe I'll call this M. So this is the Pappus reps. And this plane goes out to infinity. And then Barbeau and company found an open neighborhood on one side of this plane consisting of Anosov representations that limits to mine. And then I extended it, and I showed that you can shrink these boxes as much as you like. And their equation for the duality still works. And so they, extending what they did, you actually get an upper half space worth of discrete representations. And the ones on the inside are Anosov, and the ones on the boundary are Pappus. And the ones on the other side have an elliptic element, which you can compute. So really, this is a component. And then the prism representations, each one of these prisms has a singular geodesic. It turns out that for all the Pappus representations, they all lie on the same vertical line. And the way you do shearing is you pick the order 2 element and you sort of move to the side. And so you also get a half plane. And this also turns out to be proper. And it lands in the same space. So you have 2 proper families of representations, same boundary, and they're mapping properly into a half space. And so they're just equal to each other by a degree argument. So that sort of, like, these guys did all the work in showing that they were Anosov. They just didn't know how to go all the way to the end of this half space. And if you use some computer algebra, you can. And then the prism ones, kind of in some obvious way, you don't know they're discrete, but as groups, they do go out to the end. And then once you identify them, you can say that they're all discrete and faithful and Anosov. So this gives the complete classification of the Barbeau component of this space. The Barbeau component is the one which, there are 2 copies of the hyperbolic plane sitting inside the symmetric space X. One of them comes from SL2R as an upper diagonal matrix, and it's just the one that corresponds to lines in the projective plane. And the other one is the Goldman or Hitchin component, which corresponds to hyperbolic planes that correspond to conic sections. So this classifies the other one, the Barbeau component. Right. So yeah, so that's, and again, most of the, then it's kind of neat. Well, I don't know. Then there's like, you can sort of do. I'll say one more thing and then stop. These in the hyperbolic plane, if you shear, you can sort of move to the left or the right. I explained that like there's a line worth of shears, but the actual representation space is the line is folded over, and here these prism walls are planes, and you can either move to the left or to the right, and you actually get like a left shearing and a right shearing. And this moduli space has a kind of a foliation by left shears. You can start at a Pappus group and you can reach any other representation by a left shear. But then it also has a right shear, where you can also start. You can reach any representation by, so there's a double foliation of the moduli space by this kind of shearing rays. And then you can do you can play billiards. You can do a bounce map where you sort of go up, you shear left, and you come down, you shear right. And this gives you a kind of a dynamical system on the space of Pappus representations, and I drew some pictures. It looks like an integrable system. I mean, it seems to have an invariant function and preserve an area form. So I didn't. So anyway, that's as far as I got with this. That's it.
Questions?
Yeah.
Let's see if I understood the picture. So that means there are two components of an orthogonal presentation, the meet and the Pappus.
No, they don't meet.
Ah, no, they don't meet.
Yeah, because the other side of, so this is the Pappus ones is like a properly embedded plane. And on the other side, some parabolic element becomes elliptic. So there's nothing discrete and faithful on the other side.
Okay.
Right. I think that hitching component is sort of like, something like off, like, the other, like it's separated. That's right. Yeah.
Any other questions?
But I thought you said that there are two components of the anosoph representations. I'm talking about anosoph with respect to the maximum parabolic.
Well, what?
No, to the minimum parabolic.
I mean, one of them comes from the ones that you start with the one that preserves a line, and then these are the ones that Pappus. That's the Barbosa one. The other one is you look at the ones that preserve a circle in the projective plane or conic section, and those are the other ones. Yeah. So I just analyzed this.
If there are no more questions, let's thank our speaker again.